All right, welcome back to Materials Science. This is part 3 of a discussion that's been focused at first on bonding force curves. It led to a discussion of bonding energy curves, and now we're moving into a description of why it is that materials expand when they are heated, and how can we quantify, how can we calculate lengths of parts. All right, so as deep background, what we are pretty comfortable with, I hope we are at least, is the fact that bond energy curves have an asymmetry to them. So this is energy versus distance. At this bottom of the energy well, that corresponds to the equilibrium spacing between two atoms. As we increase its temperature to temperatures that are, if that's 0 and this is T1 and this is T2 and this is T3, if we think about the average spacing between atoms that are vibrating because they're at non-zero temperatures, the asymmetry of the curve shows us that ever so slightly the spacing between materials increases from this x0 that the spacing is at 0 Kelvin. And so if we just kind of drop that down there, we see that as temperature is increasing, the average spacing between atoms is moving to the right. In other words, the spacing between atoms is increasing. All right, so let's go from there to a formula. The principle of why materials expand when they're heated is explained by the asymmetry of the energy versus distance well. And now let's move this into something we can work with as engineers. So the bottom line is materials expand when they are heated. So if we were to take a copper bar that was 10.000 centimeters long, and we were to heat it 150 degrees C, we would observe that the bar got longer. So if the bar started off at its original length, let's call it L0, and then we heated it up 150 degrees C, we would simply observe the bar would be longer. And I'm exaggerating how much longer it would get. It wouldn't really get, visibly longer, but it would get measurably longer. So the final length of this copper bar, we could call it LF. And so LF would correspond to a final temperature, and L0 would correspond to an initial temperature. And so if we just go ahead and write it in such a way, so if the final length minus the initial length divided by the initial length of the part is the left-hand side of the equation, then the right-hand side of the equation is going to involve the term that explains or that quantifies for the material of copper how much it expands. And then the last piece of the equation we would need is that it would be related to the change in temperature. All right, I'm going to rewrite this as a change in length divided by an original length is going to equal a coefficient of thermal expansion times a change in temperature. It's kind of easier for me to think about that way. So let's just think through this equation for a moment. So what are the units of a change in length divided by an original length? What are the units of that? So if our copper piece gets a tiny bit longer, let's say 10.1 centimeters, and I subtract 10 centimeters, it's 0.1 centimeters longer, divided by 10 centimeters, it's going to be centimeters divided by centimeters, and so it's going to be dimensionless. Centimeters divided by centimeters is no dimension. So this equation is dimensionless. All right, and so what are the dimensions of a change in temperature, right? 150 degrees C minus 0 degrees C is 150 degrees C. So the units of temperature are degrees C, or degrees Kelvin, or degrees F, right? It's going to be degrees. And so therefore, what are the units of the coefficient of thermal expansion, right? It has to compensate, it has to have degrees C to the -1 in order for the equation to be dimensionless. And in fact, that is exactly what we see. So if we look up in a table, what the coefficient of thermal expansion is, and you can see in table 17.1 of our textbook, the coefficient of thermal expansion for copper is 17.0. And here's where it gets interesting. 17.0 times 10 to the -6 degrees C to the -1. Right? That's a typical coefficient of thermal expansion. All right, so we have an equation. We ought to be able to do this calculation now for copper, and let's finish off this discussion by applying this new equation that we have. So I'm going to put a box around the equation I'm going to be working on. So I'm going to be using this equation. We already have a box around our alpha. So we have our original length. This is equal to L naught. We have our delta T, because it was heated up by 150 degrees C. And so what I'd like us to do right now is to find the copper bar's length after 150 degrees C of heating. And so what do we expect? We expect it to get longer, right? It started at 10.000 centimeters, so we're expecting something a little bit longer than that. Not much, but a little bit longer. All right, so in other words, we seek, if we find delta L, since delta L is equal to LF minus L naught, and we know L naught, we'll then be able to find LF. So I'd like to solve this equation up here. I'd like to solve it for delta L. And we can do that by multiplying both sides of the equation by L naught. So that way we will have delta L is equal to alpha times delta T times L naught. Okay, and now we just got to plug in our numbers. So we're going to have 17.0 times 10 to the -6 degrees C to the -1. That's our coefficient of thermal expansion. We're going to multiply by 150 degrees C. Notice how these two units are going to cancel out. And now we also need to multiply by L naught, and L naught was given as being 10.000 centimeters times 10.000 centimeters. So this part is dimensionless. We're going to end up with a centimeter answer. That's good because our delta L will need to be in centimeters. When we run this multiplication through, we get that is equal to 0.0255 centimeters. That's our delta L. Remember, delta L is equal to LF minus L naught. So therefore, LF is going to equal L naught plus 0.0255 centimeters, which is going to equal 10.0255 centimeters. And since the original problem only gave us 10.000 centimeters, we should round this off and say that it's about 10.026 centimeters. So yes, it got longer, good, right? Good job. If it got shorter, we know we made a mistake because it was heated. And so big picture is that A, materials expand when they're heated. B, the reason is because of the asymmetry of the energy versus distance bonding curve. C, we can use the fact that it's linear, right? There's linear behavior, that the change in length linearly is related to the change in temperature. And we can use that fact to calculate part lengths at various temperatures. And of course, this assumes no phase change, like we're not changing crystal structures or anything, but that's it. That's where we wanted to get, and that's all I have.